Nuclear chemistry is all about identifying the types of emission particles from nuclear reactions and balancing a nuclear equation, which is super easy. Compared to what you've been doing, you're going to like it. It's a piece of cake. We'll also predict the nuclear decay products once we know how reactions occur. And then, finally, one last thing. There we go. Calculate the half-life of a given process, or describe what happens after a certain number of half-lives or a certain amount of time has gone by, how much of that substance we would have remaining after nuclear decay takes place. So that's where we're headed. Let's get right to it. The first thing that you need to understand about nuclear decay is that atoms come in various isotopes. Some isotopes are stable and some of them are not. But let's remember, what in the world is an isotope in the first place? Remember, an isotope is an atom that's got the same number of protons but a different number of neutrons. In other words, like carbon has 6 protons always. But carbon-12 is going to be the kind of carbon that has 6 protons and 6 neutrons. Carbon-14, on the other hand, has 8 neutrons and 6 protons. See, the number of protons is always the same for that given element, but the number of neutrons could vary, and this carbon-14 just happens to be less stable than carbon-12. So we would find carbon-14 to be more rare in living things than carbon-12. So that's what an isotope is. And some of them are stable, some of them are not. Here's how we can predict that. For anything with an atomic mass of somewhere, in the 20s, smaller atoms, then it tends to be a 1-to-1 ratio of protons to neutrons. 1 neutron for every proton tends to be pretty stable. But then once we get into larger elements, greater than 20 in their atomic number, then we need to have more neutrons to stabilize. You see, protons are positively charged and they repel one another. So we need more neutrons in that nucleus to sort of cushion that electromagnetic force that would normally push the protons away. See, these two guys have the same charge. They wouldn't normally want to be near one another, but with a neutron there, they become more stable. And in the nucleus, there's a force that binds it together, the nuclear force, which is also called the strong force, that's greater than the electromagnetic or electrostatic force that would push like charges apart or pull opposite charges together. Nuclear force is a lot bigger than that. It holds the nuclei together. So as it gets bigger, our ratio also gets bigger and bigger. So really large atoms like uranium has 92 protons. It needs to have a lot more neutrons to keep it stable. So uranium-238 is a pretty common isotope. How would you know the number of neutrons? We simply take the mass number minus the atomic number, and we can get the number of neutrons for that atom. So 238 minus 92 gives us 146 neutrons. So we can use this type of graph to help us predict whether something is stable or unstable. This is called our band of stability. Some call it the zone of stability, but it also helps us to understand what kind of decay a particle might have to undergo so that it can lie along this band of stability, so it can become more stable. That's why these reactions occur. The types of nuclear particles that we are studying in nuclear chemistry are subatomic particles, the particles that are smaller than atoms. That's because the nucleus of the atom, nuclear particles, the nucleus of the atom breaks apart into smaller things. So an alpha particle is the biggest of our smaller things. We take the helium nucleus alone. So we have 2 protons in the helium atom and 2 neutrons for a total mass number of 4. And of course there are no electrons in a nucleus, so it would have a positive 2 charge. In nuclear chemistry, though, this charge simply doesn't interest us at all. In chemical reactions, it's the electrons that react, right? But in nuclear reactions, it's the nucleus that we're concerned with, and the electrons we don't keep track of at all. So we normally don't write the charge in here. We just write an alpha particle as a helium nucleus of 4-2. Sometimes, though, it's written as just the symbol alpha with the 4 mass and the 2 atomic number. That helps us to keep straight exactly which type of particle we're talking about. Another type of decay particle is called a beta particle. And this beta particle is simply an electron that comes from the nucleus. So electrons have essentially no mass compared to the rest of the nucleus, but it has a -1 charge. So we write a beta particle like this, or we would use the symbol beta, the Greek letter beta, with a 0 and a -1. That's what a beta particle looks like in shorthand. And finally, we have a related particle called the positron. That's simply an electron that has a positive charge. And just as we normally do, if we're writing +1, we don't tend to write a +1. We would just write a 0 and a 1 with our little e to indicate it's a beta particle, but it's not a minus, it's a plus. Now, interestingly enough, if we had an electron and we had a positron, whoops, like this, then what we would see when these two add together, when they collide with one another, we would see a nuclear annihilation event, where we would get a lot of energy released and neither of those would exist anymore. Nuclear annihilation. I'm not sure that I'm spelling that correctly, but y'all can look that up later. All right, let's fix this computer so it's bugging me about this. What do you want from me? Don't show this message again. How's that? There we go. I think we're in business now, folks. Let's see what other types of particles we have then. There's also gamma rays. And gamma rays are not technically a particle. They're simply pure energy. Here's the symbol for gamma. That's the Greek symbol. They have no mass and they have no charge. It's just a high energy photon that's released as the particle moves electrons from one energy level to the other. So these are high energy photons. Where an alpha particle was fairly large, it can be stopped pretty easily because it's not going very fast. Remember how we determine the speed of things. It's the size that determines the speed, and a bigger mass means it's going to go slower than a smaller mass. Well, this has the lowest mass because it has none. So it's a high energy photon. It's hard to block that. Most gamma rays can be stopped using thick walls of concrete, but not all gamma rays can be stopped with the thick concrete, only some. Kind of scary, isn't it? And then finally we have a neutron, which you already know what a neutron is. It has a mass of 1, but it has no charge, right? And then we've got, of course, a proton. And a proton we could write with a P, and it has 1 proton and 1 neutron, or oftentimes it's written as the nucleus of a hydrogen atom. So technically it's a positively charged particle, but again we tend to ignore that sign, so you'll see it written as just a hydrogen with a 1 and a 1. In addition to seeing hydrogen, we'll often see things like deuterium, which is called heavy hydrogen, because it's got an extra neutron on it. Deuterium is the hydrogen atom that has 1 proton, but because it has a neutron as well, it has a total mass number of 2 instead of 1. And then tritium is another common isotope of hydrogen. Tritium is, come on, the type of hydrogen with a mass number of 3. See, do, and try. So we have 2 neutrons and 1 proton for a total mass number of 3. And of course only 1 proton, or it would no longer be hydrogen. So that's what makes up tritium and deuterium. And these are pretty important products when we're looking at nuclear reactions. Well, now that we know what the particles are, then predicting the type of decay is going to be a lot easier. This is summarized in your book on page 804, table 25.2. You'll see a summary of the different types of common nuclear decay processes. One type is the positron production. And remember what a positron is? It's a positive electron, right? So we would have the production of this particle with 0 mass and a positive 1 charge. So here's an example of what that might look like. Suppose that we had a nitrogen isotope, nitrogen 13, that decays into its electron, or positron that is, because it's a positive charge, and the carbon nucleus. So where we have a 1 here and a 6 here, they have to add up to the 7 that we started with. That's the number of protons that are involved here, so we have to keep that the same. Another type is electron capture. And electron capture would, of course, deal with the electrons. And if we're capturing it, well, then we're adding it to what we had. So here's our electron symbol. Let's see what we do for electron capture. We could have, say, this astatine, which is number 33. It is in the nitrogen family. And we add an electron to it. Well, when we add a -1 to a 33, that reduces our number to 32. So all of our numbers have to stay balanced, and we'll practice balancing these types of equations on a slide a little bit later on. Clear this away. There's also a process called alpha decay, where an alpha particle is produced. Remember, an alpha particle can be written as a helium nucleus, so that's our 4 atomic mass and 2 atomic number, or it could be written as the alpha sign with a 4 and a 2. Either way, it's the same thing, basically. So an alpha decay would be where the alpha particle is released when a nucleus of something large breaks apart. So, for instance, if uranium breaks into thorium and this helium nucleus, then this helium nucleus is free to go bash into something else and cause another reaction, such as a nuclear chain reaction. And here's another example where we were to take polonium, which is number 84, and it would spontaneously decompose into a beta particle, an alpha particle that is. All right, going back so I can edit. So we take polonium, number 84, and remove its alpha particle. Then we have to reduce this number by 2 so that they all add up to 84 on this side, and that would leave us with lead. So the lead and the helium would be released in this reaction. They would be the products. There's also the beta particle production. Remember what beta particles are. That's our electrons. So we have no mass. We have the -1 charge. All right, what happens when we produce beta particles? Here's an example of beta decay. If we have a carbon atom, this is carbon 14, so it's the more radioactive isotope of carbon, then it can decay into nitrogen and a beta particle. An electron would be released. But it's important that we understand where this electron comes from. So I wrote another example here for you. Suppose we have actinium, number 89, and actinium-227 decays by beta particle production into, what products? Let's see. What can I get at the top? I need to still end up with 227 total. Since I'm adding 0 to the mass, that part's easy. But what do I need on the bottom here? I need to know, what do I add to -1 to end up with 89? So that would be 90. Now let's look at the periodic table and see which element has the number 90. It's down here, down low. I need my cursor. Number 90 looks like thorium. And we write for the product the symbol for thorium, TH, because beta particle production of actinium results in the formation of a thorium nucleus and an electron. But the electron did not come from the orbitals where electrons are generally stored. And look here, we got this atomic number to go up, even though we didn't add a proton to this side. So what's going on? What happens with beta particle production is that essentially it's the opposite of electron capture. A neutron from the nucleus of the actinium decomposes and breaks apart into a proton and an electron. Neutrons and protons are both made of quarks, up quarks and down quarks, and they have 3 each. And so the nucleus has both particles, neutrons and protons, all made of the same stuff called quarks. And the neutron, not the proton, the neutron has the ability to alter its configuration into a proton if that's what makes the nucleus more stable. So the beta particle production stabilizes that nucleus by changing one of the neutrons into both a proton and a beta particle. The beta particle is released and the new nucleus is released with an extra proton in it now. So notice this carbon-6 became now nitrogen with a 7. So we have adding a proton, but not because we put a new proton in there, but because a neutron became a proton. So that's beta particle production. And what else do we have? Oh, right, gamma emission and all kinds of other things. Gamma ray productions are essentially a high energy process where we take an excited nucleus and turn it into a ground state nucleus. We saw the production of light from having an excited electron becoming a ground state electron, and we saw the wavelengths of light in the flame test. But here we're looking at an excited nucleus going to a ground state nucleus, and that's going to release a very high energy photon, higher than visible light. Remember on the electromagnetic spectrum, visible light was like 400 to 700 nanometers, and then gamma rays were higher energy, even ultraviolet or X-rays. Gamma rays is the highest that we can measure. So if we were to pass all 3 of these types of particles through an electric field, what we would see is that the alpha particle is deflected towards the positive side because the alpha particle has a 2+ charge. And the beta particles are the electrons. They have a -1 charge. So they would be deflected towards the positive side of this electric field. But a gamma particle has no charge. It's not a particle, it's a ray. The gamma rays just pass straight through it without being deflected at all. That's how we know we're dealing with gamma radiation, because it has no charge and it doesn't get deflected. Well, let's look at an important process called spontaneous fission. Any of these decays that we've been talking about where a large nucleus breaks down into a smaller nucleus is considered to be a fission reaction. So this is when large nuclei break apart or split. That's what fission is. And I've got a diagram here to show us what that would look like in a pretty common reaction. Here we go. Californium, for instance, is a common isotope used to get fission products. Californium-252 is the most common isotope, and it has a half-life of about, let's see, I wrote it down here, 2.645 years. And it just, all on its own, breaks down into lighter nuclides and neutrons, and it's produced like at the Oak Ridge National Labs in Tennessee. Californium-252 is produced as a neutron emission source so that people can use it to get neutrons for the research that they're doing, or for a nuclear reactor, wherever you might need to have a neutron shooting into something else. So californium is spontaneously going to divide. It's important to understand about nuclear reactions that these are reactions that cannot be speeded up or slowed down or turned off. They're spontaneous, and the temperature doesn't affect them. The quality of the products that they're packaged in does not affect their reactivity. It's not like adding a catalyst in a chemical reaction. You can't do anything to make these go faster, nor can you do anything to stop them from proceeding. They happen all on their own. So the best that we can do is to contain it in a useful way so that we can do work with the amount of energy that's involved here. So here's a picture of a uranium-235 nucleus that's bombarded with a neutron, and that causes it to split into smaller nuclei and more neutrons that go on to bombard with other uranium nuclei so that we can continue on in this reaction. It's called a nuclear chain reaction. I always forget to do that. Now, nuclear fusion is not to be confused with nuclear fission. Fission is splitting apart the atoms. Fusion is when we take smaller nuclei and join them together. They fuse together. So fusion is when smaller nuclei join. This is the type of reaction that occurs in the sun, and, well, technically in all stars, right? This is what makes them so hot. Here's an example. The deuterium, which we said earlier was a hydrogen with a mass of 2 and only 1 proton. So 1 proton and 1 neutron makes deuterium. And tritium would have 1 proton, of course, or it would not be hydrogen. But look, it has 3 particles in the nucleus. So it has a mass of 3, 2 neutrons and 1 proton. If these two collide, that would be a rare event indeed. Because look, we have a positive charge here, and we have a positive charge here. How do you put 2 positives together? It takes a lot of heat, that's for sure. We've got to heat this up to the temperature, say, of, the core of the sun, millions of degrees. And once we do, they have enough kinetic energy to overcome that electrostatic repulsion that would normally push these apart. If they're going fast enough, they'll collide anyway. When they do, we'll get a helium atom, or a helium nucleus, and a neutron released. Plus, we get lots and lots of energy. Nuclear fusion releases a lot more energy than nuclear fission does. So in the atom bomb, the fission reaction was used to release a lot of energy, but the H-bomb was considered even more destructive because it had so much more energy released by the fusion reaction. Cold fusion, of course, is the attempt to undergo a fusion reaction without having all of that heat. Now, I've mentioned this a couple of times, a nuclear chain reaction, and in essence, we mean a self-sustaining fission process. We could also create a chain reaction. Let's look at balancing nuclear reactions. This is the part that I mentioned was going to be super easy, and it is. So let's see how this works. Basically, we're going to make sure that the top numbers all add up to the same on both sides. So if we take 6 plus 2, which is 8, then on the other side we need to add up to 8. I already have 4, so I need to have 4 more. Now let's look at the bottoms. I have 3 plus 1 is 4, and on the other side I need to add up to 4. I already have 2, so I need another 2 here. So what element shall I write down here? Something that has a 2 for its atomic number. You may already know what this is, but I'm going to look on the periodic table and see what is the element that has a number 2 for its atomic number. And just as you might have guessed, it is helium, atomic number 2. So we write that down as our product here. Helium. So we get 2 heliums from this reaction. What type of process would we classify this as? It looks like an alpha particle is produced, 2 alpha particles in fact. So this is alpha emission. Here's our second problem. We have strontium and krypton colliding to make palladium. Well, the first thing we need to do is figure out what number goes down on the bottom. So let's look at that periodic table. And what do we find? Strontium is number 38 and krypton is number 36. So we write here 38 and 36 for krypton and palladium. What is palladium's atomic number? PD, here it is, number 46. All right. Oops. 25. There we go. This one, palladium, is number 46. All right, so now let's add these tops together. 88 and 84 gives us a total of 172. Yeah, 172. And so to find out what number we need here, we would do 172 minus 116. And that gives us 56. Wow, took me a long time to think that one through. Okay, but what is it? What sort of element is it? Let's look at the bottom numbers and see what we should have for the number of protons. 38 plus 36 adds up to a total of how much? 74. And I already have 46 here, so I do 74 minus 46 is 28. So we look at the periodic table to find out what element has the atomic number of 28. Here it is right on top. Nickel. So we put nickel, and I keep doing that. Nickel is the element that goes on the line. So this is how we predict the products of nuclear decay. We just make sure the numbers add up. The top plus the top has to equal the tops on the other side, and the bottoms on this side equal the bottoms on the right. Pretty simple, yeah? Told you it would be easy. And I was right, yeah? Yes, definitely. All right, well, let's go back and do another one. Now that we're getting good at this, let's keep going. Number 3. Calcium has an atomic number of 20. That one I know. It's, curium, I don't know. It's in the actinide series. Let's see, it's farther down. Curium, here it is, number 96. Right here. Hey, give me my pen. There we go, number 96. So we'll come back here. This is number 96. All right, the top plus the top gives us 288 on the right side. Or, yeah, this is the left side. So on this side we do 288 minus 147. And that gives us 141. All right, now let's do the bottoms. 20 and 96 together makes 116. Erase. 116. So let's figure out what samarium is so we can decide what to do over here. Samarium is not one that I have memorized. 62. Boy, that's getting cluttered. 62 for samarium. And so what do we have? 116 minus 62 leaves us 54 protons left. So let's find what element has 54 protons. Here we have xenon. So for our answer, we put xenon as our product. Pretty simple, right? Great. Let's do one last one. Oops. Okay, so this one gets a little bit more complicated. Calcium is still 20 and uranium is still 92. Did we do zinc before? Nope, we had nickel there before. So let's look at zinc, number 30. And then the neutrons that are made in this process have a 0. All right, so let's start adding the tops together. 40 plus 238 gives us 278 on top. And now when we come across here, we have 70 from the zinc. But don't forget, we have 4 neutrons. So we have to take away 4 more for those 4 neutrons because they do have mass. So that gives us a total of 204 on top. All right, then let's add the bottoms. 20 plus 92 is 112. And so on this side, we're going to take 112 minus 30. And then for the neutrons, we don't have to subtract anything at all. So we get 112 minus 30 is 82. All right, what element is number 82? Go to your periodic table and find it. Looks like it is right here, lead. So we put PB on the line. And that's how we balance nuclear equations. We're just adding and subtracting, just making sure both sides add up to the same numbers. That's all there is to it. That's not so bad, huh? Suppose, though, that all I give you is words. No symbols, just words, and you have to figure out how to write this reaction. Well, that's where you need to know what the particles are. Alpha decay, what does that mean? So first we start with iridium 174. So the 174 is our mass number that goes on top, and then we're going to look up iridium on the periodic table to see what's the atomic number for iridium. Where is this guy? IR, here we are. Down in the middle, number 77. Alright, so iridium is 77, 174 over 77. We're going to have alpha decay, and an alpha particle, remember, is that helium nucleus. So we have a 4 and a 2. So we know what the alpha particle is. Let's figure out what the next particle should be. So what do we add to the number 2 so that we can equal 77? We need to have 75 here. And on top, for the mass, we have to add up to 174. We already have 4, so the top is going to be 170. So now let's look at our periodic table and see who has number 75. And that would be rhenium. Re. So that's how we do a balanced nuclear equation when you don't have the symbols, when all you have is the words. Let's do another one. How about the beta decay of platinum 199? Remember, the 199 is our mass number, so we're going to put that up here. 199, and find your periodic table. Look up platinum's atomic number. Platinum's in the middle somewhere. Here we are, number 78, right there. So we put 78 down low. That's where the atomic number goes. And we're going to have beta decay. So that means an electron's coming off, and it has 0 mass. All right, so we can leave the mass the same, 199. And what number do we combine with a -1 to equal 78? Well, that's got to be 79. So what was the thing right next to platinum? It is gold. Hey, it's the alchemist's dream. We just made gold. There he is. See? Chemists, masters of time and space. Let's do another one. Number 3. Oh, come on. Here we are. A positron emission from sulfur. All right, sulfur 31. And sulfur's atomic number is 16. It's right under oxygen. And we're going to emit a positron. So that means it's an electron with a positive charge. So what else do we get to have? 31 on top. And if we take a 1 here, away from 16, we would get particle number 15. Let's see on our periodic table, who's got number 15? Looks like phosphorus. Of course, it's right next to sulfur because it's only 1 away. So phosphorus, there we are. These are not so bad. This is one of the easier things we've ever had to do. You know, that's why I saved it for the last thing you get to do, right? Saving the best for last. Krypton is a noble gas, and krypton 76 has the atomic number, oh, let's check, because I'm not sure. Krypton, way over here, number 36. All right, then. It undergoes electron capture. So if we're capturing the electron, we put it on this side. The -1 and the 0 mass. All right, so what are we going to get? 76 on top, and on the bottom, 36 minus 1 is 35. So what's right next to krypton on the periodic table? Let's see, number 35 would be bromine. All right then, Br. That's it. That's how we balance nuclear reactions. You guys can do this. Piece of cake. Now let's look at decay rates. When we're talking about nuclear decay, we're talking about a process that just spontaneously occurs over time. So if we're looking at the time on the x-axis and the amount of products that you have, I'm going to call it N, like for moles, on the y-axis, then we could graph how much stuff you have over time, and it would constantly be going down, down, down. Now we're going to do some algebra, because I know all you guys rock at math, and we're going to look at how to make the equation of a straight line. Where did my pen go? Here we are. So if we had a graph that looks like this, some amount of something over time. Of course, we did not have a straight line. We had decay. Whoops. Hold on to that a little too long. Well, you get the picture. We had decay. It's like exponential growth, where we have e to the x, only it's the opposite. Growth is increasing exponentially. Decay is decreasing. The opposite of e to the x is the natural log of x. So suppose that we took the natural log of the amount of products we have, the natural log of n, and graphed that equation over time. The natural log of n over time would then give us a straight line. So where n over t is a curved decay line, the natural log over t is a straight line. And I like to use the straight line because it's math that's easy. You know, I like to do the kind of math that is easy. Y'all know that about me by now. The kind of math that's easy. Here it is. The equation of a straight line is y equals mx plus b. So let's see what's on our y-axis. It is the natural log of our substance, right? The amount of substance that we're dealing with. And then m is our slope. In chemistry, that's going to be constant, so we call it k, because constant starts with k. Wait a second. Let's say it does. And it's going down, right? So it's a negative k, because it's a negative slope. And then on the y-axis is natural log of n, x-axis is time. So it's the natural log of n equals minus k times the time. And then what is b? What would your intercept represent here? Well, you know what? Let's look back at what we had before. In the slide we had before, this starting amount here represents 100% of your radioisotope, 100% of whatever substance it is that you're interested in. So in this case, 100%, we'll call it the original amount of n. So we call n sub o the original amount. That would represent the y-intercept, because that's where we start our line going down. So over time, the amount of product that we have is going to decrease at a constant rate of k. So we call that the rate constant. I know, high tech, isn't it? Constant rate? Yep, rate constant. So here's that equation again. The natural log of our substance, the amount of our substance, is equal to minus kt plus... So I can rearrange this equation to show how much is left, what proportion of my substance would be remaining here. So I get this comparison factor. How much did I start with compared to how much I have? And that's going to be equal to minus k times t, where k represents the slope of our line as it goes down over time. We can use that then to calculate the half-life, because once half of our substance is gone, then we can figure out what time it would be. Half of our substance is gone now, so what's our half-life? So the natural log of 1/2 gives us this number, 0.693, so we take 0.693 over k. Now if I were you, that's something I would put on my note card for this test. Any of these equations that you don't think you can remember, which in my case would be all of them, I would be putting those on my note card, in addition to all the different types of decay particles, the alpha and beta and gamma and all that fun stuff. Because I don't expect you to have that memorized, I just expect you to know how to use that. Then we can calculate the rate of this reaction based on how much stuff we started with and what's the slope of that line. So how fast the reaction proceeds depends on your original amount and the decay constant. That's all there is to it, but it will make a lot more sense when you see me do it. So let's look at a problem. Here's example 1. Technetium-199 is used to form pictures of the internal organs in the body, and it's often used to assess heart damage. So if the rate constant for technetium-199 is known to be 1.16 times 10 to the minus 1 hours, then what is the half-life? Here's what we want to find out. Here's the half-life of this nuclide. So let's see what we get. Remember our equation for half-life? T1/2. Oh, get my pen back here. T1/2 is equal to 0.693 over k. And in our problem, we were given k equal to 1.16 times 10 to the minus 1 hours. All right, well, I want you to see me putting this into my calculator, but let's see, what numbers do we use? 0.693 divided by 1.16 times 10 to the minus 1. All right, I had 0.693 divided by my decay constant, 1.16, use your E button, to the minus 1, and I get 5.9741, all those numbers. Let's only keep 3 of them because my decay constant only had 3 sig figs. So 5.97 then, huh? All right. That wasn't so bad. Give me my writing back. 5.97, and these units are hours, so our units for time for the half-life is hours. So if they were to inject this into your body to see if you had heart damage, like a blockage in one of your arteries in your heart, then it would be decaying with a half-life of 5.97 hours. So by the time you get home from the doctor's office, then most of it's already gone. No big deal. That's why they use things with a small half-life, and they don't put very much in there anyway. Let's look at another kind of problem we could do. The half-life of molybdenum is 67 hours. So now they're giving us the half-life. And the question says, how much of a 1 milligram sample of molybdenum-99 is remaining after 335 hours? So it's more than 1 half-life, way more. We're going to have to go back to this equation where we know that the natural log of what we have over what we started with is equal to minus k times t. That comes from our equation of the straight line. And let's identify, what do we know? We know what the T1/2 is, the half-life, right, was 67 hours. And we can use that then to get k. If the half-life is equal to 0.693 over k, and we solve for k, multiply across and then divide, so we're trading places with these, we just do 0.693 divided by 67. Alright, so get your calculator out and do this as I solve this. You need to work through these too. So 0.693 divided by 67, push pause if your calculator's not out. Push pause and turn on your calculator right now. Okay, I get 0.0103. Alright, so there's my K. What was my original amount? Let's see, I had 1 milligram to start with. And what I want to find out is how much do I have left now after 335 hours have gone by. So let's get started solving this problem. I have my natural log of what I want to know, I'll call that x, divided by 1 milligram is equal to minus k was 0.0103 times my time, 335 hours. Alright, so I have the natural log of x is equal to negative, where is it? Oh, yeah, I didn't do this math. How do we undo the natural log? We have to use the inverse. E to the natural log of x just gives us x. E to the x is the inverse of natural log. Just as division is the inverse of multiplication, e to the x is the inverse of the natural log. So we then take the other side, e raised to the negative 0.0103 times 335. Let's show that with the calculator so that you can see how I put those numbers in. So back to the calculator and clear the writing for now. Calculator on. That's always a good place to start. We need the button that says e to the x. It's right where the natural log is, the ln, some people call it. So we push second ln to get e to the x. Then we're going to type in what we had there. We had a negative. Now I'll use parentheses. And we had 0.0, oh, I forget. Gotta look at my numbers. Right, 0.0103. Some of you guys were already on top of that. Had it all worked out. Okay, so I had 0.0103 times 335 hours. And that's all in parentheses because I want e raised to the product of those two numbers. Hit enter, and we get the amount that's left now is 0.0317297, blah, 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 blah. We only get to keep 4 sig figs there. So 3173, it looks like. Here's where we want to be. 0.0317 milligrams. That's the amount that is remaining after 335 hours. Be careful. Sometimes they tell you such and such is remaining, or they want to know how much of it has decayed. So if we want to know how much has gone away, we would subtract 1 milligram minus 0.0317. So be careful of the wording of the problem. Let's look at another one. A wood artifact from a Chinese temple has carbon-14 activity of 24.9 counts per minute compared with an activity of 32.5 counts per minute for a standard zero age. Counts per minute is simply the ticks on a Geiger counter. So if this is describing activity, radioactivity, then counts per minute at 0 is comparable to the counts per minute now, because when the item that was made from wood was a tree. It was taking in carbon dioxide and incorporating it into its body structure. When it died, it no longer did this anymore, so all of the carbon then began to decay radioactively and not getting replenished by new carbon dioxide coming in. So that's what we're looking at, is now we have less activity, so we can compare activity just as we were able to compare mass or number of moles. So we're still going to use that as our N number for comparison's sake. So what do we know about this? We know that we have these number of counts, so we'll call the N now 24.9. And the N that we start at, N sub 0, would be 32.5. And we have a half-life given to us of 5,715 years. And for half-life we call it T1/2. We want to determine the age of the artifact, so how much time has gone by since this object was no longer a tree. So we won't really be able to say when the artifact was produced. We could simply say that we know how long ago the tree died that the wood was made from. But at least that gets us some sort of estimate, right? Assuming they chopped down the tree to make this artifact. So we are going to use our equation. The natural log of our amount divided by our initial amount is equal to minus k times t. Well, we don't know k. We better come back and solve for k. K is equal to 0.693 over T1/2. And T1/2 is 5,715 years. So what do I get for k? That gives me 1.2 times 10 to the minus 4. Alright, so let's start putting things into our equation. For n, I'm going to use what I've got now, 24.9 clicks on my Geiger counter. And what I started with, 32.5 clicks on the Geiger counter. And that's going to be equal to minus k, so negative 1.2 times 10 to the minus 4 times t. And t is what I'm solving for. So in the calculator, let's do this part first. I'm going to be taking the natural log of what number? The natural log of 0.766 equals negative 1.2 times 10 to the minus 4. And then we're solving for t. So what I need to do is divide both sides by the negative 1.2 times 10 to the minus 4. Do that over here. 1.2 times 10 to the minus 4. Alright, be careful how you put this into your calculator. We have to take the natural log of 0.76 first. So, clearing out my writing here real quick so you can see what I'm up to. So the natural log of 0.766 is negative 0.2665 something something something. Okay, now we're going to divide that by our negative 1.2 times 10 to the minus 4. Please use the E button. Don't use times 10 with the little hat thing. Alright, here's my time, which gives me the age of my artifact, 2,221. Well, what do we got? How many sig figs here? 3 sig figs. So we'll call that 2,220 years old. That's how old that artifact is. So that is quite a long time ago, isn't it? 2,220 years ago. That's how long ago the tree died so that we could carve that wood into an artifact. Well, sometimes a half-life question is way easier, and I put this one on here just to show you an easy way. Notice, the half-life of iodine 131 is 8 days. How much of our 100-gram sample will remain after? 32 days. Well, 8 goes into 32 evenly, so I'm going to show you a simple way to estimate this. And we're going to make a chart. My initial mass was 100 grams at a time of 0 days. So on day 0, I had 100 grams of my sample. And after 8 days, how much did I have left? 8 days is my half-life, so I had only 50 grams left after 8 days. And then 8 days more go by, and my amount drops by half again. So now I have only 25 grams left. 8 more days go by, so now we're on day 24, and I have half again, which is 12.5, and then we get to 32, which is what our question is asking for, right? After 32 days, half of this is reduced again, so I get 6.25 grams, and that's the answer to my question. How much will remain? Only 6.25 grams remain after 32 days. So if it's as simple as making a little chart, then let's do it the easy way, and you won't have to bother with the equation with natural logs and e to the x and all that good stuff. All right, well, let's finish up with looking at some applications of nuclear chemistry. Why is it that scientists get all excited about nuclear chemistry? Well, one application is dating. And I don't mean like finding a prom date. I mean telling how old an object is, like we did with the Chinese artifact. Carbon is commonly used here, carbon-14 in particular, because once an object dies, it doesn't breathe in or take into its body any more carbon by breathing or by eating or whatever. So if something was once living and it no longer is, we can predict how long ago that object died using carbon dating. Medicine is another important application. We use radioactive dyes because it provides a contrast to what's already in your body. So you may have to drink a barium milkshake so they can see what's happening in your gastrointestinal tract. If you have some sort of problem or blockage or something that they want to see what's happening inside you, they put a dye that's radioactive so they can trace it as it moves through your body or through your heart or whatever they want to look at. Another application is in weapons. The nuclear weapons tend to be very destructive because they release a tremendous amount of energy. I'll take you through the calculations in just a minute so you can see how much energy, but we're talking for atom bombs on the order of 180 mega electron volts, and then for fusion bombs or hydrogen bombs even more than that. And finally, we have the energy application. If we need energy from fossil fuels, then we have to keep buying more oil. Well, if we use nuclear power in a nuclear power plant, we can get a lot of energy for just a little bit of material. So I'd like to show you how that works. Let's look at the energy in particular, because a nuclear reaction gives us a lot of energy. Here's how. Let's look at the formation of an oxygen nucleus. You already are familiar with oxygen. It's number 8 on the periodic table. So it's made up of 8 protons and 8 neutrons in the nucleus. Of course, there's 8 electrons too, but let's focus on just the nucleus. There's a phenomenon known as the mass defect, that when an atom forms, it loses mass. So let me show you what we mean by this. The mass of a single proton is 1.67262 times 10 to the minus 27 kilograms. Very tiny mass, but about 1,800 times larger than the mass of an electron. So it is significant. We're going to have 8 of these in an oxygen atom. All right, so get your calculator and multiply this through 1.67262 times 10 to the minus 27 kilograms times 8 protons per oxygen atom. Now let's do the same for the neutrons. The mass of a single neutron is 1.67493 times 10 to the minus 27 kilograms. So it is slightly larger than a proton, because remember, the neutron can break down into a proton and an electron. Remember that in the neutron or the electron capture? So the neutron's a little bit heavier than the proton. All right, so we've got this all multiplied through. Now we're going to find out what is the sum of these. If we add these it's 16 particles, right? Add these 16 particles together, and I get a total mass. If we were to conserve the mass, we should end up with 2.678704. Go ahead and keep all of your digits for now. We'll worry about sig figs later. Times 10 to the minus 26 kilograms. That's what we expect to find for the mass of the nucleus of an oxygen atom, is this much. If we were to add the mass of 8 protons and 8 electrons together, then we should get exactly this much. Well, in reality, here's what the mass of an oxygen atom is. Remember that mass of that oxygen atom comes from its protons and its neutrons, not from its electrons. So here's our mass, 2.65535 times 10 to the minus 26 kilograms. We predicted 2.678704. Somewhere along the way, we lost some of the mass, and that's what the mass defect is. And losing mass generates a lot of energy. As Einstein's famous equation predicts, it's really delta M, the change in the mass, that produces the energy. And so let's find out what was the change in mass. Do final minus initial, as we normally do. So let's take this minus this, what we thought we'd get, minus what we actually get. What's our change in the mass? Get your calculator out and subtract these. Let's make sure that you can put these numbers in correctly. 2.3354 times 10 to the negative 28 kilograms. That's a pretty significant difference. This change in mass is almost on the same order of magnitude as an entire proton or an entire neutron. So that energy we should take into consideration. Let's see how much energy that would be. So by the mass defect of the oxygen atom, we're looking at then how much energy. So our change in mass was 2.33, only one of my 3's showed up, 54 times 10 to the negative 28 kilograms. Get this into your calculator. And if I'm going too fast, just hit pause and catch up with me. Get this written down. All right, and then c is still the speed of light. And we're going to round that to 3 times 10 to the 8th meters per second. And that number is a big number and is squared. All right, so that's the amount of energy that we're looking at. Go ahead and calculate this through. I get 2.1 times 10 to the minus 11 joules per atom. Is that right? Yeah. 10 to the minus 11 joules. And this is per atom. For every atom of oxygen that forms, we get 2.1 times 10 to the minus 11 joules. Maybe that doesn't seem like all that much, but remember, that's just for a single atom. Let's calculate how much energy that is per mole. So we take 2.1 times 10 to the minus 11 joules. And that's joules for just one atom. That should be a negative sign there. So I'm going to put this in a T table. Joules per atom. Per means it goes on the bottom. And in 1 mole, how many atoms are there? You got it. Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. Now we're getting to some big numbers, aren't we? So that's going to be equal to, get your calculator going, 1.27 times 10 to the 13 joules per mole. And just to put this into perspective, we'll compare it to something else that you're familiar with. So I'm going to change this to kilojoules per mole so that we have a fair comparison. That would be 1.27 times 10 to the 10 kilojoules for every mole of oxygen formed. So far, so good? All right, so let's look at this number of kilojoules just as a result of the mass defect, that as the oxygen atom is formed, some of its mass is lost. Let's compare that to the burning of methane. The methane in the Bunsen burner, it burns with an energy of negative 882 kilojoules per mole. And all of you who've just completed thermochemistry, you might recognize this as our heat of combustion for methane. So if we are going to compare this amount with this amount, then take 1.27 times 10 to the 10 and divide by 882, negative 882. All right, so again, 1.27 times 10 to the 10 divided by negative 882 kilojoules per mole. And this would be negative 2, of course, because that energy is released and exothermic reactions have a negative sign. Yes, of course, Miss Gray. Yeah. So what do we get? Here's what I get. I find that the mass defect gives us an energy that is 14 million times more energy from a nuclear reaction than from the chemical reaction of the combustion of methane. That's tremendous. 14 million times more energy is a prodigious amount of energy. So look why scientists care so much about this. If we have a nuclear power plant, then the fuel we use to heat up the water in our power plant, I don't know if you've ever seen how a power plant works. Basically, we heat up the water turns into steam, the steam flows through to turn the turbine, and the turbine turns the generator, which is a wire that's in an electromagnet, and then it sends electrical power through the power lines to everybody's houses, right? And we get to use it to do work at home and at school and everywhere else that we go. So a power plant basically uses hot water to move things around, and then of course we have to cool the water back down again, and so we have a couple of different circuits. We have this circuit here for the steam to get hot, and then it boils this steam in this circuit as it comes through here and turns the turbine. Then it's going to get cooled again by the condenser, the cooling water coming through our cooling tower. It cools it down again, so then once it's cool, we pump it back in to get heated up again. So basically, we want a circuit where nothing from the reaction is ever in direct contact with anything from the outside environment, and that's what we get in a nuclear power plant. We just want to get the steam to turn the turbine. It's kind of like a windmill. In the good old days, you turn the windmill using the wind power, and it makes the generator turn around, and we get electrical power. And that's how wind power still works today. But in a nuclear power plant, the thing we use to turn that turbine isn't wind, but rather steam that has been heated by a nuclear reaction. This works the same way if we were to put coal in this furnace and heat up the water by burning coal, or by burning natural gas such as methane, propane, butane, and some of those guys. And what kind of energy were we looking at here? Negative 880, what was it, 881? 82. Don't want to shortchange it. 882 kilojoules per mole for burning fossil fuels. And for a nuclear power, I could have 14 million times more energy. So, in other words, think this through. If we have 1 ton of coal, that's 2,000 pounds of coal to burn in our coal burning power plant, then to get the same amount of energy, I would need 14 million times less of my nuclear substance, of my radioactive substance in my nuclear power plant to get the same amount of energy. That's significant because that would produce a lot less waste than burning 2,000 pounds of coal. And how many tons do you suppose are burned in a traditional power plant every year? Plus, with nuclear power, there's no greenhouse gases emitted. The thing that we do have to worry about, however, is what to do with our spent fuel rods, because they're still going to be hot and radioactive when we're done with them. So most of it can be recycled, but there's that approximately 2% of that waste that cannot be recycled, and we have to figure out now how do we protect ourselves and the environment from this radioactive waste, and where are we going to put it and what do we do with it. So nuclear power is something very exciting to scientists, particularly in the time of this troubled economy where the price of fuel and oil continues to rise. Well, folks, that's the end of our podcast, because that's the end of our year in chemistry. Thanks so much for playing along.